All right, gentlemen, today we're going to be talking about the different bisectors that are going to appear in triangles, some of the relationships between them, and some new terms and things that we could do with these types of bisectors. So first things first, we got a couple terms that we're going to talk about. So the first term is concurrent, and concurrent means when three or more lines intersect at one point, they're concurrent. So if you look over to the image on the bottom right, we have line RS, CD, PQ, AB. All those lines meet at point O, and that point where all the lines intersect is called our point of concurrency. So I say again, these lines are all concurrent, and the point of concurrency is at 0. So this is going to be useful and necessary information when we start talking about our different bisectors inside of triangles. Now, here is a new theorem. So it's called the concurrency of perpendicular bisectors theorem. So this states the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. So just read that once or twice. I'm going to pause the video, write it all down, and let's talk about what I have written at the bottom. So I ask, please pay special attention to how this diagram is created with perpendicular bisector. These perpendicular bisectors are in red. So as it says underneath the little symbols category, it's PX, PY, and PZ. Those are perpendicular bisectors. We know they're perpendicular bisectors because they form a 90-degree angle and they split the line in half. For example, if you look at the right side of the triangle, PY cuts AC in half because AY has 3 tick marks and YC has 3 tick marks. The next part of this states that all these blue dotted lines are all equal in length, and that is the length from the vertice to what's going to be called the circumcenter. And we'll get that note on the next slide. Okay? So these lines are made using the point of concurrency and the vertice. And this point, using the perpendicular bisector, is called the circumcenter. Okay? So circumcenter, once again, the point of concurrency of the perpendicular bisectors. This point is equidistant, so equal distance to each vertex, and the circumcenter may be inside or outside of a triangle. Now we're going to see a visual of that in the next slide, but let's keep on going. So now I have this term circumcised, or circumscribed, not circumcised, circumscribed about. So if I say something is circumscribed, we can use the circumcenter to create a circle. So that red dotted circle is a circle circumscribed about. That's how we say that phrase, the triangle. So basically it means it's drawn around and it's touching all the vertices, and the circumcenter is the center of the circle. So we'll get a little bit more in detail of this later on in the year, but it's still good to know now. Here's what I'm talking about when our circumcenter could be on the outside, inside, or even on the triangle. So if I have an acute triangle, which means all my angles are less than 90 degrees, it's going to be on the inside. If I have a right triangle, that circumcenter is going to appear somewhere on that hypotenuse. If I have an obtuse triangle, it's going to appear on the outside. So note that these perpendicular bisectors, they go on forever in each direction. They keep going. If we look back at this image, we have arrows on all the blue lines going up and down, left and right, so they keep on going. So that's why it can appear on the outside as it does in the obtuse. So let's look at an example. So our example states that P is the circumcenter of XYZ. Okay, so now we want to find what PZ is. So what do we know about PZ? What do we know about these distances to vertices? If we pop back up here and look at our concurrency of perpendicular bisectors theorem, we know that if we have a circumcenter, which we do as it says, we're going to be talking about perpendicular bisectors, and so we know that the distance from that circumcenter to the vertices is going to be congruent. That's why we have PA is equal to PB is equal to PC. So coming back down here, I know that P is going to be equidistant to vertices X, Y, and Z. And we can also say that PX is congruent to PY, which is congruent to PZ. So what we can do is we could set all these equal to each other. We could set PX and PY equal to each other, and we can solve. I'm going to leave the rest up to you. It's just a simple system of equations. I want you to go ahead and solve for what PZ would be. So pause the video, go ahead, work out what it is, and then circle your answer. I will be looking for this. If you do not circle your answer, I will be very disappointed, and if you don't have the answer, you will not get full points. Okay? And we keep going. So now we're going to have kind of not necessarily the opposite, but now we're talking about angle bisectors. So this states the bisectors of the angles of a triangle are concurrent at a point equidistant from the sides. Okay, from the sides of the triangle. Once again, I ask you to pay attention to how the diagram is made. The red lines are the angle bisectors, and we can tell this because of the angle marks. We have the up at angle B, it's split in half, A is split in half, and C is split in half. So that's how we know that they're angle bisectors. And now the blue lines are all equal measure as well. Okay, so that's where we get the PX is equal to PY is equal to PZ. So this point of concurrency is going to be different for angle bisectors and perpendicular bisectors. It has a different name. Okay, so there's a couple terms, and there's going to be a little bit of a curve to getting to be familiar with all these terms. And these terms are the incenter. So this new point with the angle bisectors instead of the circumcenter is called the incenter. So all it is the point of concurrency, so where those three lines meet, of the angle bisectors. And we have a new term. Instead of saying we have circumscribed about, we have inscribed in. So the incenter is always going to be inside of the triangle. Definitely missed a word. So the incenter of the circle. Oh, so we say the incenter is the center of the circle that is inscribed in the triangle. So now this time, our circle is inscribed in, meaning it's kind of on the inside of the triangle. If we go back up top, you can see that this circle is on the outside, and I get a slightly clearer picture here. So the difference between inscribed and circumscribed. So pay attention to that. We've got key differences there. Now let's look at an example. So I say that point P is the incenter of triangle FGH. So I have this relationship if the measure of TFP, so that's like the top left angle, and UFP, that's like the top right angle, we have those measures, and we want to find the value of X. So the first thing that we note is that P is the incenter, meaning that this is the point of concurrency of the angle bisectors. So what does that mean? That all of our angles at our vertexes, so F, G, and H, those angles are bisected into two parts of equal measure. So using this information, we know that those two angles that we have measures for, this 3x plus 15 and the 5x minus 13, we know that those two angles are going to be, the measures are going to be equal because they're congruent, because that angle F has been bisected. So I started off for you. I give you guys a little bit of a hint as to how to set it up. Once again, I would like you to solve for x. I guess I should have also said find what the angle measure is. So if you find what the angle measure is, that would also be nice too. I should have been more specific. But, so circle your answer when you're done. Other than that, be prepared to come into class tomorrow, ready to work. We're going to do more practice problems. And that's all I got for you guys today.